Okay, so we're in chapter 8. We're talking about intermolecular forces. And as a background or preview to intermolecular forces, on class last Wednesday, we did all of the review material that was on this first page of the chapter 8, number 1 in class activity sheet. So this comes from chapter 5. We assigned electronegativity values. We determined if a bond was polar. We determined if a molecule was polar, and then we're able to look at individual formulas and determine from those what the structures are and determine from those whether the molecules are polar or non-polar. You guys remember how to do all this? This is all the background really that we've got that we need for this section of chapter 8. And by the way, this is the background, this is the section of chapter 8 and from chapter 5 that is directly applicable to our Chemistry 1120 class. So if you're planning on taking Chemistry 1120, this is the in-class activity sheet that I would take and I would do and I would practice in preparation for Chemistry 1120, actually. At least for my class, it would be helpful for sure. Okay, so here we go. Lecture 8.4 on intermolecular forces. So we just talked about gas laws, and what are the fundamental tenets of the kinetic molecular theory that contributes to properties of gases is that the molecules are so far apart that they do not attract or repulse one another. They have no dealings with one another in particular. So, for instance, and I know we've done this 3 or 4 times, but we're going to do it again. Here we go. If we look inside a microscope, and this is what we see. If we look at a solid, we'll see individual particles that are packed really close to one another and they're fixed in their positions. If we look inside our microscope at a liquid and we were able to see individual pieces, we would see individual particles that are packed really close to one another, but they can still move and slide past one another. So there's still flow. And if we look at our gas, we might see 1, maybe 2 little gas particles zooming quickly on their way from one place to another. So hopefully you can see these guys are just really far apart. They're not interacting with one another. These guys are close enough together to actually touch one another. And these guys are, again, close enough together to actually touch one another. And so then what we find is that there are a number of things which we call intermolecular forces, or in other words, forces that occur between molecules, which predict physical properties of solids and liquids. So physical properties, for example, include things like melting point and boiling point and vapor pressure and solubility in water and surface tension, these kind of things that we can really easily see in the macro scale. These properties are based entirely on the kind of forces that these atoms or molecules feel between each other. So, and to start, this shouldn't be really terribly surprising to you. We're talking about types of intermolecular forces. Let's look at, I'm going to do this kind of from strongest down to weakest. Strongest to weakest. Intermolecular forces. So first of all, the very strongest, and I won't call these intermolecular forces, but maybe interparticle forces, are when an ion is attracted to another ion. We call that ion-ion interactions. Where might we see ion-ion interactions between particles? Okay, so Megan says when we have a metal that's bound with a non-metal, you would find ion-ion interactions because what happens when metals and non-metals get together and make bonds? What kind of bonds do they make? Ionic, yes, that's exactly what I was looking for. So ionic compounds, and Megan was right. You're going to kind of identify ionic compounds when you've got a metal bound to a non-metal. When you've got that, you know you have an ionic compound, and ionic compounds are held together by the interactions between positively charged ions and negatively charged ions. This is a really strong bond. Positive ions attract negative ions. They're very, very attracted to one another, okay? So properties of this attractive force that we find are that they tend to have very high melting points and boiling points relative to other types of compounds that we're going to address here. We also find that they are brittle. And this is because our positive ions and our negative ions line up to make these extended crystalline structures. In fact, I'll put this down, crystalline. They tend to be crystalline, where they're maximizing all of their positive and negative interactions. And if you just kind of tap it on one edge, you can misalign those interactions and end up aligning a positive with a positive, and then all of a sudden they repel one another and burst apart. So that's why they're brittle. So we look at brittle as something whereas if it experiences a small fracture or a small stress, then it might just pop right apart. It doesn't stick together very well. But they are brittle, they're crystalline. Great example of an ionic compound. Any of you guys think of a good example of an ionic compound? Salt, yes. You've got the metal sodium when it bonds with the non-metal chlorine, which, by the way, of course, when they bind, then it's no longer a metal and a non-metal, but it's a sodium ion, which has different properties, with a chlorine ion, which has different properties. And the properties, as for example, I've told you, ionic compounds have very high melting points and boiling points. We find that sodium chloride is going to melt at 800 degrees Celsius. That's huge. That's so high. But that's just a good example of how strong these ion-ion interactions are. Basically, when you're trying to melt something, you're disrupting the positions that they've got as a solid. And by doing so, you're disrupting this positive to negative charge attraction. So that's how much energy it takes. If I'm just going to pump heat in it to try to get it to move, that's how much heat it's going to take to disrupt these interactions. Okay. So those are ionic compounds. Covalent compounds then have different intermolecular forces. And we actually break these out into three different categories. So covalent compounds, we have polar covalent, we have non-polar covalent, and we have polar covalent where specifically we have a hydrogen bound to either a fluorine, an oxygen, or a nitrogen. Okay. opposite. There we go. We'll fix that. How do you identify a covalent compound? Kind of similar to how we identified ionic compounds. What would you be looking for? Like every time you see a metal bound to a non-metal, that's a really big clue that it's an ionic bond. How do you know if you're looking at covalent bonds instead? Two nonmetals, perfect. This is just a throwback to chapter 4, okay? So two nonmetals. Yeah, I guess chapter 4 for the 7th edition, chapter 5 for the 6th edition. Okay, so two nonmetals tells you it's a covalent bond. And then how can you tell if it's polar or nonpolar? You guys remember? Electronegativity. So differences of electronegativity will tell you if your bond is polar or nonpolar. You apply that to the Vesper shape, and that'll tell you if your molecule is polar or nonpolar. Okay, if your molecule is polar, then you are subject to something we call dipole interactions. And this is where you have basically molecules with a dipole. That's why they're polar. So the difference between hydrogen and chlorine is 0.9, so that's enough to make it partially polar. Okay. So then these are going to arrange one another. They're going to line up so that the partially positively charged end of one molecule is going to be attracted to the partially negatively charged end of the other molecule. So it's a lesser version of this, like the ion-ion interactions is a full +1 charge attracted to a full -1 charge, maybe even +2 and plus and -2 charges. But here it's just a partial positive attracted to a partial negative. So it's a weaker attractive force, but it's still based on the same idea that opposite charges will attract one another. And that makes sense. If you've got a whole bunch of little dipoles in a jar, they're like little magnets, and they're going to stick together where they're magnetic. They're going to line up to where their magnets are attracted to one another, and they're going to stick together like that. Okay. It's the same thing with polar molecules with the H attached to the F, O, or N. The difference here is that it's just a much stronger interaction, and so we're going to give it its own category. So covalent polar molecules, which have a hydrogen bound to a fluorine, oxygen, or nitrogen, are subject to what we call hydrogen bonding intermolecular forces. It's a terrible name for an intermolecular force because when I read hydrogen bonding, it sounds to me like it's talking about something which is just bound to hydrogen, but it's not. It has to be one of these three atoms which is bound to hydrogen and therefore has a polar bond and therefore will network with one another in three dimensions in exactly the same way that these do with dipoles. So for example, water is a good example of our hydrogen bonding because it's this bent molecule, the OH bond is polar. So altogether the molecule ends up with a partial positive on the hydrogen side and a partial negative on the oxygen side. And same as below, those partial positives are going to be attracted to those partial negatives. And so you end up networking these oxygen atoms with hydrogen atoms from other molecules. And they actually end up being so thoroughly networked, you can't even tell which hydrogen belongs to which oxygen anymore if you looked at that, if you were able to look at the molecular level of water. So very strong intermolecular forces. Here's a way you're going to remember hydrogen bonding versus dipole-dipole. Hydrogen bonding is fun. It's so fun. You'll always remember it because it was the funnest thing in this whole chapter. Oh, I'm not even getting pity laughs here, am I? No pity laughs. Okay, thanks, Jackie. Okay, non-polar covalent molecules then, they don't have dipoles. So there's nothing that's going to attract them, the part of one molecule to a part of another molecule. They're just like not interested in each other. So nonpolar molecules are only subject to what we call London dispersion forces. They're also called van der Waals forces. They're also called induced dipole interactions. I'm not going to have you memorize all those names. I'll just test you on London dispersion forces. But they're really weak because there's no sort of attractive forces between them. And so really what we call dispersion forces or induced dipole forces, we're essentially saying we've got these two molecules, they have no separation of charge as we did above. Let's say we've got two chlorine molecules. We could say that, maybe just due to the random nature at which, electrons move back and forth between these chloride atoms, maybe there could be a temporary dipole that arises just by the fact that these two electrons are spending more time at this guy's house at the moment, and that temporary dipole might induce a temporary dipole in its neighbors. I mean, it's obviously kind of a weak argument for what might even start to keep these molecules together. But there's really very little that's going to attract one chlorine molecule to another chlorine molecule. So if you could think of these molecules that are polar as being little magnets that stick to one another because the magnets line up, you could think of your nonpolar molecules like little marbles. They don't stick to each other at all. I mean, they could be a solid, sure, they could be a liquid, you could swirl them around in a bucket, but they're not sticky. They're not attracted to one another. Okay. So if it helps to envision these guys as like those little magnet balls that you get in toy kits, and think of these guys as little marbles. That'd help you predict the properties. Can you guess the properties of our polar covalent molecules versus our non-polar covalent molecules? Oh, hang on a second, Robin. So to determine which of these we've got, you're going to first determine if it's ionic or covalent, and then if it's covalent, determine if it's polar or nonpolar. And if it's polar, then look for H attached to FON, right? So if it's ionic, then you could immediately say it's ion to ion. If it's covalent, you could say it's one of these. If you determine that it's non-polar, you could automatically say a dispersion. If you determine it's a polar molecule, you look for the FON. If it's got it, it's hydrogen bonding. If it doesn't, it's dipole-dipole. Properties here. Megan, you're welcome, Robin. Megan says polar stuff would tend to be crystalline. Yes, some of these, particularly the hydrogen bonding, because it's such a strong attractive force that they really, especially when they form solids, they want to maximize all of those intermolecular forces. So what we find is that some covalent molecules tend to be crystalline. For instance, sugar and ice are good examples of molecules with hydrogen bonding that form crystalline solids. Whereas others, which have no such attractive forces they need to maximize, aren't crystalline at all, like wax would be a good example of a solid, an amorphous solid that comes from a nonpolar covalent molecule. So great, Megan. I'm not going to say hard and fast these ones are crystalline and those are not, but I will say that these ones might have a higher chance of being crystalline, whereas these ones would have a much greater chance of being amorphous. Usually amorphous, very low melting points, boiling points. I'll say very. These ones would be moderate melting points and boiling points. These would be lower melting points and boiling points. So for example here, water has a melting point of 0 degrees Celsius. If we look at the other examples that I gave here, HCl has a melting point of, I don't remember this, I'm looking it up super quick. Melting point of minus 114 degrees Celsius. Okay. And Cl2 might even have a slightly higher melting point because it's heavier. Minus 101.5 degrees Celsius. Let's try H2. Has a melting point of minus 259 degrees Celsius. There we go. (259 degrees Celsius. Is that what I said? 259? Yeah. 259 degrees Celsius. Okay, so hopefully you guys can see from the examples given here. By the way, you don't have to memorize these numbers. These are given to illustrate the point. The ionic solids have much higher melting points and boiling points. And this is what I mean by much higher, I mean 800 degrees Celsius higher. These all have lower melting points, but among this group of covalent compounds, a polar molecule with hydrogen bonding has a much higher melting point than a polar molecule without hydrogen bonding. And a polar molecule with or without hydrogen bonding is going to have a much higher melting point than a non-polar molecule of approximately the same size. Okay. The other thing to add to this properties list is with respect to melting points and boiling points is that these interactions are also based on size. That is to say, a larger molecule has a larger surface area with which to interact. So if I've got molecules that have the same intermolecular forces, like two molecules which both have London dispersion forces, but one molecule is very small, so it has a much smaller surface area with which to interact, and one molecule is very large, therefore it has a larger surface area to interact, then the larger molecule will have higher melting points and higher boiling points because it's harder to break those interactions, even if they're weak, okay? Which is why hydrogen was minus 259 versus chlorine, which had a melting point of minus 101 degrees Celsius. Okay, Cl2 weighs 70 atomic mass units. Hydrogen only weighs 2. So being 35 times bigger by mass then is going to increase your boiling point and your melting point. I hope that makes sense. The other thing to note here that I want you guys to be able to predict is solubility. When we talk about solubility, we're usually talking about solubility in water. So which of these molecules with these intermolecular forces, which do you think would be the most soluble in water? Obviously important because we live on a planet that's loaded with water. We're biological creatures that are built on water. 70% water. Almost all of our chemical reactions that make our bodies run occur in water. If you want to deliver a drug via IV, it better be soluble in water because that's what your blood is made of. So what kind of things here would be easily soluble in water? What do you mean by Cl? Like, are you talking about the Cl2 molecule? Are you talking about the Cl ion and sodium chloride? I'm not sure what you mean there. All of them are going to be soluble to some extent, but some are going to be much, much more soluble than others. So for example, and here's what you need to look for, essentially. You guys know that water is a polar molecule, a very polar molecule. It's subject to hydrogen bonding. Okay. And so it's going to attract other molecules. It's going to interact well with other molecules which have charges. In other words, if I'm an ionic compound and I've got charges, well, this little partial negative is going to be attractive to this positive charge. This little partial positive is going to be attractive to the negative charge. So water will easily dissolve ionic compounds because my charges in my water interact well with the charges in my ionic compounds. So this would be soluble in water. Almost all ionic compounds are soluble in water. There are exceptions. We memorized those in chapter 5, I think. Other molecules with hydrogen bonding, I hope you'd see water would be soluble with water. Other molecules like water would also be soluble in water. What about dipole-dipole, like HCl? Do you think that'd be pretty soluble in water? You've got partial charges. Are those partial charges going to interact well with my partial charges on the water? Yes, they will. They'll totally be soluble. Oops, running out of space here. Soluble. Okay, what about lead to dispersion molecules? We've got no partial charges. Is that going to interact well with the partial charges on the water? Or to put it another way, if given a choice, do you think water is going to interact with another water molecule, or do you think it's going to interact with lead to dispersion? Okay, Jay Houston is right. Water's not going to interact very well. There's just not attracted to it. It's not afraid of it. They don't hate each other. They have nothing in common. They're not interested. If we look at these as marbles, and we look at this, if we look at the polar molecules as magnets, and we look at the nonpolar molecules like marbles, you can guess if we put magnets and marbles in the same jar and shook them up, what would happen at the end of the day? What would you end up with? You'd still have marbles and magnets, yes, but would they be all evenly distributed with one another? Or would the magnets all clump up on one side and then the marbles would be excluded from the magnets? Yeah, you could totally picture this. At the end of the day, I mean, even if you made this little thing and you very carefully said, I'm going to disperse my magnets, these are red magnets, really far apart from one another, and I'm going to put marbles in between them and on top of them so that they don't start next to one another. So the blue is my marbles. Okay, so you put a bunch of marbles and you specifically use those marbles to separate the magnets. If you guys have these at your house, you should try it. Anybody that's got kids might have those little magnet toys with the sticks and the balls that are exactly what you do. So you take this and then you swirl it around, swirl, 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 swirl. By the time you're done, I hope you guys can visualize and picture that what you're going to have is all of the magnets clumped together, because as soon as they get close enough together, they'll snap together because they'll be attracted to one another. And then all of the marbles are going to be surrounding it, I mean, basically excluded from this little magnet party. Everybody Does everybody see that conceptually? Does anybody see that conceptually? Yes, okay, good. This is exactly what happens when I take something polar, a little magnet, like say water, and I put it with something that's non-polar, or little marbles, like say oil. Oil is non-polar. We can shake it up and get them all mixed up together like we would at a good vinaigrette. But if I let it stand for long enough, what's going to happen with my oil and my water if I let it stand? They're going to separate. They're naturally going to separate because every water molecule will attract other water molecules next door, like my magnets snapping together, and the oil molecules will just be excluded from that party. And so as a result, we find that our nonpolar molecules are not very soluble. We could say not soluble, although we can measure exactly how not soluble they are, but really not soluble, generally speaking. Oil and water, they're going to separate. Okay. So I hope, does this chart make a little bit of sense, understanding based on the polar or ionic or nonpolar properties of a molecule, which you could already predict. You can dictate what kind of forces they'll be subject to, and that's going to help you predict what kind of properties you'll expect to see. That's what we're doing on our 8.1 in class activity sheet. That's chapter 5 from the 6th edition, chapter 4 from the 7th edition, by the way, for the review. So we're on section 5. So the first section is just tell what kind of intermolecular forces they're subject to. If you could tell me whether these are ionic or covalent, that's the first step. And then if they're covalent, if you could tell me if they're polar or non-polar, that's the next step. And if they're polar, if you could tell me if they have hydrogen bonding or not, that's the third step. So if there's a little flow chart, you would say it's ionic, that it's subject to ion-ion intermolecular forces. It's covalent, then you have to ask yourself, is it, hang on a second. I don't know if you guys like flowcharts, but if you like flowcharts, then here we go. If it's polar, we have to do something else. If it's non-polar, we're going to say London dispersion. If it's polar, we have to ask ourselves, does it have H bound to FON, in which case it's hydrogen bonding. If it does not, then it is just dipole-dipole. So let's work through just a few of these together and see if we can answer those questions. For LII, would that compound be subject? That's an ionic compound or a covalent compound? It's an ionic compound, so according to our flow chart, we just say that's subject to ion-ion interactions. That was easy. Okay. All right. Next, F2, is this ionic or is this covalent? Okay, covalent. Then we ask ourselves, is this a polar molecule or a non-polar molecule? Oh, Jackie, you're way ahead of us. Jackie's exactly right. It's non-polar. You could tell without even drawing the structure, because all you've got is fluorines, and when a fluorine bonds with a fluorine, the difference is going to be 0, so it's automatically non-polar. So you could go ahead and assign that this is only going to be subject to London dispersion forces. Yeah, no, that's great. What about this one, NaCN? Is that ionic or covalent? That's ionic, because sodium's a metal, Cn is your polyatomic ion. One reason I have you memorize, I want you to be able to recognize those real quick and say, ah, that's an ion. So ionic compound, easy. Ion-ion intermolecular forces. Okay, HCN, is that ionic or covalent? Covalent. Okay, now we have to ask if it's polar or non-polar. And since we have different, some of these could, so we might have to draw out the structure. I'll do this for you to save you some time. Structure of HCN looks like this. Difference between hydrogen and carbon is 0.4, so that is not a polar bond. Difference between carbon and nitrogen is 0.5, so that's a very slightly polar bond. It's going to look a little bit like that. So based on that structure, what kind of intermolecular forces is HCN going to be subject to? Jay Houston says hydrogen bonding. Anybody agree or disagree? Can explain why? Shada says dipole-dipole. Do we have a tiebreaker? Oh, okay. Guys both agree it's dipole-dipole. You are right. Dipole-dipole because it is covalent and it is polar, but the hydrogen here is not bound to the fluoride, oxygen, or nitrogen. Here that hydrogen is stuck on a carbon. So it's not hydrogen bonding, but there is dipole here. So that's going to be dipole-dipole. Excellent. Okay, that's how we're going to do section 5. I want you guys to finish section 5 on your own. We'll cover the results in class on Wednesday. And let's look at section 6 here. This is arrange compounds by boiling point. Remember, the stronger the intermolecular forces, the higher the boiling point. The weaker the intermolecular forces, the lower the boiling point. So for weak to strong intermolecular forces would solve this question. Or if they have the same intermolecular forces, then the smaller molecules have a lower surface area, so they would be lower boiling points. And the larger molecules have a greater surface area, so they would have higher boiling points. So the first question to ask is, among this group of molecules, what intermolecular forces are they subject to? Arrange them in that order, and then for those which have the same intermolecular forces, arrange them by size. So help me out with this one here. Actually, I'll give you guys just a couple minutes to look at that. Tell me how you would arrange that from lowest to highest, and tell me why you used that method. Yeah, for size, you could just look at molar mass. So Shada noticed that they all appear to have the same types of intermolecular forces because they all look like the same type of molecule. Every single one of those has only carbon and hydrogen bonds. But when I say that, I mean only has carbon and hydrogen atoms. They do not have hydrogen bonds. None of those would have a hydrogen attached to fluorine, oxygen, or nitrogen because None of these ones in this first row have a fluorine, oxygen, or nitrogen, right? Yes, exactly. But you're right that they have the same intermolecular forces because their structures are so similar, right? They've all got carbon and hydrogen atoms. What kind of intermolecular forces would they be subject to? Robin and Jay Hughes did both say dipole-dipole. How'd you come up with that answer? They are covalent, yes, and you know that there's no FO or N, so your options are London or dipole-dipole. So we could draw out the structures and look at our differences, but before we do that, let's just look at the differences. In molecules that only have carbon and hydrogen atoms, my options are carbon-carbon bonds, which would not be polar, and carbon-hydrogen bonds, which have a difference of 0.4, so those are not polar either. None of these molecules has a polar bond in them. So you don't even have to draw the structure to know that they would then be led to dispersion forces, all of them. So this is one where I'm saying, hey, look, we've all got the same intermolecular forces. So then you're going to have to look by size or molar mass, essentially. And you don't even have to really add that up. It's easy to eyeball this and say, okay, a molecule with 4 carbon atoms and 10 hydrogen atoms is going to be bigger and heavier than a molecule with 1 carbon atom and 4 hydrogen atoms. I hope you guys can see that. So on that basis, then, how would we arrange that from lowest to highest boiling point? Which would be the highest? Perfect. C4H10, highest. What would be the lowest? CH4. Okay. Second lowest? Like this guy right here. This is our highest, that's our lowest. Between these two, which one's going to be lower? Perfect, C2H6. And then we'd have C3H8. You can see I go from 1 carbon to 2 to 3 to 4, 4 hydrogens to 6 to 8 to 10. In every way, these molecules are getting bigger, so they're going to have increasingly greater boiling points. Okay, let's do this one. First, look at intermolecular forces because that's a much stronger effect. I'd arrange them by that. And then if any are the same, then go by size. So among these 4, we have H2O, and ACl, CH4, and C2H6, which is going to be the very highest. Excellent. Sodium chloride. Because sodium chloride has ion-ion intermolecular forces, and that's the very strongest. Okay, what would become next? Let's use that one up. among those which remain. I've got water, which has hydrogen bonding, and these two which have London dispersion forces. So I'm going to say water is the next highest. The last two are just London dispersion, so them we can rank based on size. What's going to be the very lowest? It's going to be the smallest. Perfect. CH4. Therefore, we'll have C2H6. Okay. Again, for this section, first go by the strength of your intermolecular forces, and then if they're the same, go by size. All right, I'll let you guys try this one on your own. Bring it to class on Wednesday. We'll check our answers. We've got this last section here, which talks about properties of solids. And so far on our other page, we already talked about the properties of ionic solids and covalent solids. So this chart that I did here is basically could be copied and pasted directly over for covalent type solids and for ionic type solids and for covalent type solids, both. We do have two other solid types that we want to introduce you to or remind you of and kind of explain why they have the properties that they do. So I'm going to actually just solicit on the in-class activity sheet. You could do it with me. And we'll talk about these ones. So we know we've got ionic solids are held together with ion. So the ions is my smallest unit. That ion attractive force is what holds those together, those individual ions together. Properties, we know that ionic compounds have very high melting points, boiling points. They're brittle. They're crystalline. For example, with sodium chloride, right? 800 degrees Celsius melting point. Okay. Covalent solids. Smallest units are of a covalent solid. Actually, hang on a second. I'm not going to call this a molecular solid because my smallest unit is a covalent molecule. My interparticle forces would then be hydrogen bonding, dipole, or London dispersion forces. Could be one of those. I'm just going to say intermolecular forces because it's going to be one of those. And then the properties, we've got low to moderate. Melting points and boiling points. Sometimes they're crystalline, sometimes they're amorphous, so it's hard to say. Good example of water, 0 degrees Celsius, melting point. Okay, so there's two others that I want you guys to be familiar with. One is a metal, so like a metallic solid. Obviously, metals are not ionic compounds and they're not covalent molecules either. Metallic solid. You guys know some of the properties of metals because we talked about them when we introduced the periodic table. We were looking at different sections of the periodic table. They are malleable and ductile. They conduct heat and electricity. Heat and electricity. They're shiny. And their melting points are also kind of at a range, right? Because you've got mercury, which is a liquid at room temperature, so it already has melted. And then you've got some like titanium, which have really high melting points. So they're kind of all over the board. I'm not going to put a melting point out here. Smallest unit of a metallic solid is an individual atom. And these are held together with something we call the electron C model. And let me put this out over here. This will help you explain kind of why we've got these properties versus, say, our ionic compounds. So our ionic compounds, we've got this network of positively charged ions and negatively charged ions. And this network goes on in 3 dimensions. So there's 2 dimensions. So you can hopefully visualize our ionic solid here. Our metallic solid, we've got individual atoms, and we know that metals don't particularly want the electrons that they have. That's why they give them up so easily to form ionic compounds. So when we have a whole bunch of metal atoms together, essentially those electrons that are on the surface end up kind of occupying the communal play yard. So here's this nucleus, this house, what atom house, and the kids are just all out playing. Okay, so the electrons are all just out there. They're close enough to the nucleus so that they could say, yeah, that kid's mine, kind of a thing. But far enough away that the nucleus kind of doesn't care which of these children are his, so long as that they're around. As a result, then we can push electrons in one side of this metal, and then that they're just going to displace these other electrons. We're going to pick electrons out. This is why metals conduct electricity so well. Okay. It's also why they conduct heat so well, because each of these pieces can move really well in their positions without disrupting really a strict crystalline shape. Like here, if I tried to get these to move, I would be disrupting this carefully crafted crystalline shape. It's also why they're malleable and ductile, because if I hammer this into a thin sheet, or if I draw it into a long wire, I'm just rearranging the size and shape of that electron C. Whereas if I tried to do that with my ionic solid, if I tried to hammer it at a position, I might misalign these attractive forces, and then they would be repulsive forces instead of they'd break apart. That's why ionic compounds are brittle versus metallic ones, which are exactly the opposite. Does this kind of make sense? It's also why they're lustrous. When light comes in, they get reflected by those surface electrons, and they're shiny. That's why they're shiny. It's like seeing electrons. It's kind of fun. So we obviously don't talk a lot about metallic bonding in this class, but just to give you an idea, this is why metals have the properties that they do versus ionic and covalent compounds. The 4th solid type you guys need to know is something called a covalent network. Covalent network solid, the smallest unit is an atom, but all atoms are held together with covalent bonds. It sounds a lot like our covalent molecules, but it's different in that in a molecular solid, you have individual molecules, like, say, water molecules, that are then networked with these just attractive intermolecular forces. Whereas in a covalent network molecule, I have atoms that are networked with actual covalent bonds in all directions. It's like the covalent networking bond version of an ionic solid. Okay. So as a result, then, if you watch to bust up this network, you have to break covalent bonds. Covalent bonds are really, really strong. This is just an attractive force, but there's like legal ramifications to breaking this bond. Okay, so so far as the molecular world is concerned. So as a properties here, we're going to have extremely high melting points and boiling points. These woods are definitely crystalline because they're very fixed in their positions. They're also really hard, very hard. What does it sound like I'm describing here? Hardest substance in the world. It's a crystal. Would be really hard to like melt it. Yeah, that's a diamond. So our diamond is our classic example of a covalent network solid. That's exactly what it is. Do you guys know at what temperature it would take to melt a diamond? So we could compare it to our water and sodium chloride. It's crazy high. It's like, I don't know if it's even in my lecture notes. Let's see here. I don't think it is. It's like 3,500 degrees Celsius. Yeah, that is the question. In order to determine this, somebody had to have taken a diamond and melted it, right? That had to have happened. There's a bunch of scientists got together. They wanted to investigate properties of diamonds, pooled all their money and bought a tiny one, and then they melted it. And they discovered it was 3,500 degrees Celsius. And actually, it didn't melt, but what it did was decomposed into carbon, coal, basically. It turned the diamond into coal because diamonds are a covalent network of carbon atoms, so that it just turned from the diamond form of carbon to the coal form of carbon. Which sounds like a tragedy, doesn't it? But if you're a scientist, then A, you learn something new. So for science, you have to do it this, Paul. For science, that was exciting. But if any of these were good businessmen, and that's not always the case, scientists don't always make good businessmen, but if they were, all you have to do is find a wealthy financial backer and say, we have proprietary evidence which shows that diamonds are made out of coal. And if you will finance my studies and investigations, then I can maybe come up with a way to turn coal into diamonds, and you'll be a very wealthy person. And then that scientist could have been taken care of for the rest of his life, investigating diamonds and coal in the lab, if he was a good businessman. So it's not all a tragedy, or it doesn't have to be a tragedy, but in this case, a little bit of a tragedy, maybe a little bit. Anyway, so that's a covalent network solid. And again, that's different from a molecular solid, is that they both have covalent bonds, but a molecular solid is individual tiny molecules with covalent bonds that are attracted with intermolecular forces, whereas a covalent network is just covalent bonds in all directions. So that is it for our lecture on intermolecular forces. I'm going to stop this.